how big is the entire universe? And the short answer to that question is we don't know. And under the laws of physics as we currently understand them, we might never know how big is the biggest thing there is. Having said that, you might have seen some numbers knocking around in answer to how big is the universe. From 28 billion light years across to 93 billion light years across, and that it's infinite. So in this video, I'm going to explain where do these first two numbers come from and what do they actually represent, and then also explain why saying that the universe is infinite is also incorrect. So let's start with that first number there, 28 billion light years across. Or technically, more accurately, 27.6 billion light years across. Now this number refers to the most distant thing that we could physically ever see and sets the size of what's known as the observable universe. Now that's because light travels at a set maximum speed in a vacuum of 299,792,458 meters per second. That's around 1 billion kilometers an hour in like normal everyday units. Now the universe itself is only 13.8 billion years old, which means that the maximum distance that any light from an object could have traveled in that time is the distance that light travels in 13.8 billion years. Now, if we handily define a unit called the light year, being the distance that light travels in a year, it's around about 9.5 trillion kilometers, then the maximum distance that we can actually see anything out to that light has had enough time to travel to us from is 13.8 billion light years. That's only in one direction though, from like our vantage point here on Earth. We can see 13.8 billion light years in any direction. So the total diameter of the observable universe is 27.6 billion light years, which is often rounded up to 28 billion light years across. So if that's the furthest that we can ever physically see because light has this maximum speed limit, then where does this much larger number for the size of the universe of 93 billion light years come from? Well, although that maximum distance that we could ever see anything at, 13.8 billion light years away, is set by the light travel time, we have to remember that in that time that the light has been traveling, the universe itself has also been expanding, moving apart us here on Earth and any object that emitted that light. It's this expansion that actually allows us to work out how much the light has been redshifted by to, these longer wavelengths by the expansion, and therefore how long the light has been traveling for and then get a distance. So when we measure the redshift, we can then get at a distance. But when we do that, we're measuring the distance between us here on Earth and where the object used to be when the light was emitted, and not where that object is now, billions of years later after all that expansion. But knowing how far away that object was and knowing the rate of expansion, having measured it, allows us to correct that number for the expansion. So for example, JWST just confirmed the distance to the most distant galaxy known, GSZ 13. The light from which has been redshifted by a factor of 13.2. That means the light from that galaxy that we're only just detecting now has been traveling through the universe for 13.48 billion years. And so we're seeing that galaxy as it looked 13.48 billion years ago in the early days of the universe. So we could say that the galaxy GSZ 13 was 13.48 billion light years away when the light was emitted. But to know the distance of that same galaxy now, we need to correct for the expansion. And working that out for this galaxy, you get 33.3 billion light years away. Now we call this the co-moving distance as opposed to the look-back distance, the distance you calculate from the look-back time, i.e. the light travel time. This is why us astrophysicists just stick to redshift when we're talking about distant objects, right? It's just one number that you have to quote and there's no confusion. Plus, that translation of redshift to look-back distance or co-moving distance changes depending on what rate of expansion that you measure, and there's lots of different experiments giving us different rates of expansion as well. I've talked about this a lot on this channel before. It's known as the crisis in cosmology. I'll leave a few links in the video description down below if you're interested in hearing more about that. But just like for our galaxy GSZ13, we can work out the co-moving size of the observable universe. Its look-back size, or diameter, is 27.6 billion light years. But if you correct for the expansion of the universe, its co-moving diameter is 93 billion light years across, which was the second number in our list. But what about that last possibility in our list? The actual size of the whole universe is infinite. Not just what we can see in the observable universe, but in the parts of the universe where light hasn't physically had enough time to travel to us yet, because the universe is only 13.8 billion years old. But therein lies the problem. Light hasn't had enough time to get to us yet, so we can't get any information about those parts of the universe. We can't see it and we can't observe its effects, so we can't know. You know, in the same way that we can't know what's beyond a black hole's event horizon because light is all trapped in there and we can't get any information from it. The edge of the observable universe is also like a horizon that we can't see anything beyond, we can't get any information from, and therefore we can't put a number on how big is the entire universe. Our cosmological models of, okay, what's the geometry and the topology of the universe and how much total energy does it have contained in it might one day be able to tell us. But until then, we kind of just have to accept the fact that we don't know how big is the biggest thing there is.